Hello, I'm Juan Carlos Curi and I'm going to talk about deep learning. I'm a Master of Science of Computer Science with a major in machine learning, graduated from Georgia Tech. I'm a computer engineer and a senior mentor of 7 Udacity nanodegrees of artificial intelligence. Here is the list of nanodegrees I'm mentoring. Deep learning is just a set of algorithms and techniques to train artificial neural networks in order to learn patterns from data. Artificial neural networks are very simplistic models of biological neurons. The simplest model of a neuron is a perceptron. A perceptron receives inputs from other perceptrons. Such inputs are multiplied by the corresponding weights, which represent the strength of synapses or connections. The weighted inputs are summed, and if the sum surpasses some threshold, the neuron is activated and outputs a strong signal. Neurons can be connected in many ways, but the most common way to connect neurons is by using layers. The input layer receives vectors or tensors and propagates signals to the next layer, and so on. Layers compute signals until they reach the output layer, which computes the final results. The loss function measures the error in the association between inputs and outputs. The error is the difference between the actual outputs and the predicted outputs computed for some specific inputs. Once we program the loss function, we plug it into the gradient descent algorithm in order to minimize the error. It's difficult to draw a multidimensional error function in which each dimension is one of the multiple weights and the result is the error. But we can draw an error function with two weights and the error. The gradient descent technique makes the weights evolve from higher regions of error to lower regions of error. Neural networks are just homeomorphisms, or projections from higher dimensionality pattern spaces toward lower dimensionality feature spaces. Usually, the original pattern is not linearly separable, but the projected feature space is linearly separable. Features are learned from data. Features are not manually engineered by humans. Neural networks act like a funnel that compress inputs and produce a condensed output of salient features. Let's analyze the expressive power of neural networks. A single layer can represent linearly separable frontiers. 2 layers can represent convex open regions. And 3 layers with a sufficient amount of neurons can represent any kind of pattern. That's what the Cebenko's universal approximation theorem is all about. More than 3 layers help to create even more complex abstractions, hence the name deep learning. In machine learning, we have 2 types of classifiers. Discriminative classifiers model the frontier that divides classes of patterns. Such frontier is modeled by using a few parameters. Generative classifiers model the stereotypes of classes of patterns. Such stereotypes are modeled by using more memory. Neural networks are very successful and popular because they are both discriminative classifiers that model the frontier and also generative classifiers that model the stereotypes by using just a decent amount of parameters. When introspecting the stereotypes learned by neural networks, we notice that stereotypes are smoother, more flawless, more average, and more beautiful than actual patterns. That's the case of synthetic voices and eigenfaces based on PCA. Neural networks are a form of nonlinear principal component analysis of PCA. When we perceive an actual pattern that resembles our learned stereotypes, we perceive those patterns as beautiful because they cause less neuronal resistance. Whereas, when we perceive an actual pattern that differs from our learned stereotypes, we perceive those patterns as ugly because their unusual, out of the norm traits cause more neuronal resistance that make our brains try to digest and to understand such unusual out of the norm traits. That's how we can define beauty in mathematical terms. And that's the end of the presentation. Thanks for your time and attention.